Hello world, this is Craig. Today let's look at the details on how to use the Willem programmer to get our program or our data from the Hex file into the EPROM and using the Willem PCB6.0 programmer. I'm going to break this down into 4 parts. The first one is the settings, the software hardware settings for the Willem programmer itself, and then how to program a base EPROM, which is different than programming an expansion EPROM. And we'll see when we look at the memory of the system what the difference is between those two. And then we're going to look at, kind of as a bit of an aside, the Intel Hex file and how that works to get the data into the EPROM programmer software to begin with. The programmer comes with a little Windows application. You install it and set it up. And this is basically what you see when you open the application. It allows you to select a device, and we're going to go to EPROM 27XX, and we're going to select the 2732, which is what the SBC85 board uses. It gives us this little diagram of how the jumpers need to be set. Now, one of the problems with making a universal programmer, and this programmer can take all the way from a 2716 all the way up to a 4 megabit EPROM. And those all go in the same socket, and the problem with that is that some of the pinouts are different. And so that's why this programmer has got a bunch of jumpers and a bunch of dip switches, and those are to set up the socket to program the device that we want. So for the 2732, the programmer is set up right now, and we can see that the dip switches along here and this jumper J3, as well as J1 and J2 are all just to get the pinout correct for the 2732. So you can see when the 2732 is inserted, it's justified at the bottom, leaves the empty space at the top, just like in the little diagram. And we have this jumper J3 and all the dip switches set to match the diagram. Same with J1 and J2. I did on my programmer actually touch the top of these dip switches with a red Sharpie, make it look more like the diagram and just easier to see at a glance that it's set up for the right device. So all of those are just to set up for this socket and that device. Now there's 2 other things we have to set up. The first is this programmer can have 4 different voltages for the VCC. Typically we will have this set for 5 volts. To do 5 volts we have J5 installed. And then if J5 is installed, then we have to look down here at J8. J8 can either be in the lower position, which is 5 volts. It could be in the upper position, which is 5.6 volts, or it could be completely removed, which is 6.2 volts. We could also just completely remove J5, in which case the VCC would be 3.6 volts. So we can have any of those voltages, 3.6, 5, 5.6, or 6.2, depending on how J8 and J5 are configured. For the 2732s, those are all 5 volt VCCs, so J5 will always be installed and J8 will be in the lower position. In the last video I said that the USB connection was only for the power, and that was only suitable when you were using programming, the lower programming voltages, and that I incorrectly remembered. You can use the USB power for any of the programming voltages, but you can't use it for any of the VCC voltages. So you can use the USB power if you have the VCC set for 3.6 or for 5 volts. So basically in this configuration right now, we could use the USB for power. You can see I'm using the barrel connector for the power. But if we wanted to use VCC as 5.6 or 6.2, then we can't use the USB connection. We have to use the barrel connector. So I incorrectly said that it depended on what your programming voltage was. Doesn't matter what the programming voltage is, it only matters what VCC is, whether or not you can use the USB connector. Okay, so the third thing we have to set is the proper programming pulse voltage for this device. And we can see if we look at so to set up the VPP, or the programming pulse, we have to use these 2 jumpers. We've got J6 right here and J7 right over here. From our diagram, it says what position we put J7 and J6 for whatever voltage we want. We can see that for 12.5 volts, we would have one up, one down. For 15 volts, we would have them both down. 21 volts, we would have them both up. For 25 volts, we would have J7 down and J6 up. So you can see right now I have it set up for the 21 volt 2732A, so I have both J6 and J7 in the top position as shown in this little diagram right here. So we're going to presume that everything works the first time. All we have to do is plug in the programmer and then plug in power either from the USB port or from the little barrel connector. We have to hang this on a parallel port, and we choose what parallel port we have it set at. LPT1, 2, or 3, and on this little computer I've only got the one parallel port, so I have it set for LPT1. Then the next thing we want to do is check to make sure that our hardware is actually working. We go up to the help, click on test hardware, and you can see down here at the bottom it says hardware present. So it went out, it did a simple communication, and it was able to communicate with the hardware. So now to program the base EEPROM, all we have to do is open up the file. So we go to our file and we're going to open up the Hex file, and I have right here, this is Dave Dunfield's monitor 85 that I've ported over to this piece of hardware. So we open up the Hex file. We can go down to the bottom. Next to the device tab is the buffer tab, and we can see that it has opened up that Hex file and brought it in, and we can see that entire Hex file in the buffer. So here we go from address 0000 all the way up to 0FFF, and we can see that there's only 2 bytes left in this EEPROM that aren't full for this monitor. Now we can check to make sure that the EEPROM is blank. So we click on the question mark and it comes back and it says the device is empty, which is what we want. Everything is set up, we're ready to go, so we just click on the program chip. Takes it just a few seconds, it programs the chip, and then it's going to do a verification to confirm that it was programmed properly. Comes back and says device programmed OK. So now this program, Dave Dunfield's monitor 85, is in the EEPROM, ready to go into the board. If we wanted to, we could verify that what is in the EEPROM matches what is in the buffer. So we can click on this verify button. It's going to compare the EEPROM to what's in the buffer, and it says device verify OK. Another thing that we can do is read what is in the EEPROM. So let's go ahead and read it in. And it read the program back, basically the program that we put into it. It read it back. We could verify, but of course it's going to work because we just read what is in that. So let's open our file again, and we can click on a memory location, and this little window opens. It says edit in Hex. Unfortunately, there's a little bug in the program, so we can see what address is there, but we can't see what the data is. But we can click on the tab to go down to the data, and then we can change that. So let's put in a 20 where it used to be 10. Now let's do a verify, and it says there's an error at address 13. The chip says 10, but the buffer says 20. So this is good, that if something went wrong with the program and if you've got a bad cell in your EEPROM, it will tell you that there's an error when it does the verify. And it would also, obviously, if the EEPROM hadn't been erased properly, it would give you an error. So that's all there is to programming an EEPROM when the EEPROM is in the base socket. But if the EEPROM is in the expansion socket, or if you have an expansion board somewhere up in higher memory, it gets a little bit more complicated. To understand the difference between programming a base EEPROM and an expansion EEPROM, we need to look at the SBC85 memory, or memory in any system for that matter. There's 2 ways that we need to think of any memory location that's on a device or a system like the SBC85. So we can think of any location as having a system address, and that same location has a device address. So for the SBC85, our system address from 0000 to 0FFF belongs to this base EEPROM. So anytime that the system sees this first digit is a 0, it says, I'm going to enable this EEPROM, and then this EEPROM is going to respond based on the bottom 12 bits. So if we're anywhere from 0000 to 00FF, it's the same for the system address and this device address, because this device has an implied 0 at the beginning when it's decoding the bottom 12 bits. If we go to the next 4K up, we jump over into the expansion EEPROM. And for this, the system says anytime that this first digit is a 1, I'm going to disable everybody on board except for this EEPROM. And then this EEPROM is going to decode the bottom 12 bits. And again, it's going to go from 000 to FFF. And as that decodes the bottom 12 bits, it'll put those onto the bus when it's being referenced. The next address up, the system dedicates from 2000 to 3FFF to the RAM. And again, the RAM address for this device is going from all zeros to 1FFF. The system decodes the first digit, and it says if it is either a 2 or a 3. And then the device itself decodes the bottom 13 bits, and it decides which memory location to access. Finally, for this, we have the 8155, which starts at 4000 and goes up to 40FF. For that particular device, it sees its address is going from all zeros to FF. So once it's selected, when the most significant digit is a 4, 0, it will select this 8155. And then the 8155 will put its data onto the bus between 0 and FF. If we have an expansion card, maybe it has some more 2732s, let's say that we have one up at 70 that goes up to 7FFF, and another one from 80 and goes up to 8FFF. But again, just as before, let's say those EEPROMs would be selected when the first digit is either a 7 or an 8, and then they would be responding to the bottom 12 bits. The reason that's important is when we are programming an EEPROM, the software for the EEPROM programmer is thinking in terms of system memory when it opens up the hex file, because the Intel Hex file will tell the programmer exactly where every byte belongs according to the system memory. But when it is writing to the device, it's now thinking in terms of device memory, which is only as big as the device. And in this case, the EEPROM programmer device memory will go from 000 to FFF. If we had a bigger device, then it would have a larger range, or a smaller device would have a smaller range. But basically, we have to tell it how to get from the system memory up to the device memory, which always starts at 0. The programmer can't do this by itself because we could be using these EEPROMs in various ways. We could have them odd and even, for example. If we had interleaved memory, we might have them side by side if we're doing 16-bit words. And so they're both accessed at the same time. And so this would be the high byte and the low byte. So the programmer doesn't know any of that. And so it relies on us to transfer the data from how it's addressed in system memory according to the way that it received it in the hex file over into the device memory. So basically all of these one by one have to be taken from that system memory to there, or that one to there, and so forth. They've all got to be shifted up so that they wind up in the proper place for that EEPROM. Let's look at a program that's designed to go into the expansion RAM. So this is the confidence test that I have for the SBC85, and it has an org statement here that places the program at 1000. So let's open that with our programmer. We open up the hex file. So it looks like it didn't open up the file properly. But we need to remember that the programmer is thinking in terms of system memory. So it's opened up that file, but it has actually placed that in the memory location that the file told it to place it, which is up at 1000. And this buffer doesn't show us what's up at 1000, but it's actually there. And we can see that it's actually there by picking a different device. So let's open a device that is bigger. So let's pick up let's go all the way up to a 27512. That'll show us the full 64K of the memory. And so we can see that this goes up, and here's our program. We can see at 01000, this is where our program starts. So everything from 000 up to 0FFF is for what's in the base EEPROM. But here our program starts at 1000 and will go up to 1FFF. There is a little bit of stuff down here. This is the version number of that software, and I meant to have that up in the expansion EEPROM also, but it was left over and left it down in the base EEPROM. So basically our program here then is starting at 1000 and going on up. If we were to program the EEPROM like this, it wouldn't put our intended program into the EEPROM. It would just put in all of these Fs. So it would just skip our program entirely and just put in what is there from 000 up to 0FFF. So what we have to do is we have to offset it. We have to tell it to take whatever is in the system memory location from 1000 to 1FFF and move it down to the lower portion where our EEPROM is in the socket. Now what we should be able to do is, if we go back to the device page, we can see there's a hex offset. With most programmers, what you can do is type in what the offset is from the system memory to the EEPROM memory, and so we should be able to type in here that we want to have the offset of 1000 hex, and would bring that down by that 4K so that the address that is 1000 in system memory would now become an address of 0000. Unfortunately, that doesn't work in the software. So there's two problems. One, this offset hex goes the wrong direction, so this would actually move it up 4K, and even if that worked, it would crash it. So if we tried to move this 4K, it'll just crash it and we have to restart the software. If we wanted to put in a minus 1000, well, unfortunately that doesn't work either. So my advice is just leave that at 0 because we're going to find a different way to move this program. What we're going to do is this A to B copy. So we're going to copy from the memory location up at 1000 down to the memory location starting at 0. So let's click on the A to B copy. The A address, that's our starting address. We want that to be 0x1000. Where do we want that to go to? We want that to go to 0000, so basically down where the EEPROM is. And how much do we want to copy? We want to copy 4K, which is 1000. Now we click on the Move A to B. We now go over and look at our buffer. And we can see this is our program. Our program has been copied from where it is in completely decoded memory down to where it will be in this particular EEPROM. We have to remember this was a destructive copy. So what was down in this location before is now gone. If we wanted that back, we have to reload this file. But if we had a sequence of EEPROMs and we had to move them all down to program, we would one at a time have to copy from 1000 down to 0, and then we would have to copy from 2000 down to 0, and 300 down to 0, and so forth. If we were programming EEPROMs that were contiguous in system memory, but now they're individually have to be moved down to 000. So let's go ahead and program that. The first thing we have to do is go back to our device. Now, I just changed from the 2732 up to the bigger one to show you the buffer. We really don't have to switch. This was up in memory even if we can only see a part of it. So to demonstrate that, let's open up the file again. Here's our all F's. Let's move it down. It remembered that information from before. We say move A to B. It copied it from the upper memory, which was there even though we couldn't see it in this buffer. We can then put in a new EEPROM and program it. So if all you're interested in programming the base EEPROM, you could have stopped watching this video a long time ago. If you're only interested in programming the expansion EEPROM, you can stop watching now. But if you want to see where this all comes from and how this comes together, we're going to take a little bit of a diversion into where this hex file came from and what the hex file looks like. Let's go back to Dave Dunfield's diagnostic monitor. So this is the monitor itself, its source file, and the actual code starts right here, startup code, kick off the monitor. So this is the very beginning of our program. Now we take this program, we put it into an assembler, the assembler kicks out 2 additional files. The first file it kicks out is a list file. We can line these up and we can see that the list file has all of our text that we had before, the entire program, but it has added some columns over here on the left hand side. The first column is our program counter, or it's our memory location. This is actually where each byte is going to be in memory. So we can see right here, this is at 0000 is where we have our org statement. The first thing that goes into memory is a 31, and then a 6140, and so forth. Up here we're at address 0008, that's going to be a C3. We can jump down here, 0044, that's going to be an E3, and so forth. This is all of our memory locations, and these are the data, either program or a data that goes in that memory location. The second thing that the assembler kicks out is the Intel Hex file. And so let's look at the Intel Hex file for Dave Dunfield's monitor. So this is the Hex file. You can see it's just a text file you can open up with Notepad or any text editor. And this is the file that the programmer is going to open and read and then take the data from this file and put it into memory. So everything the programmer needs to know about the data and where it is in memory is located in this Hex file. So let's look at the Hex file. Each line of the Hex file begins with a colon. Then there are 2 digits. We can look up here, 06. That means that this line of the Hex file has 6 bytes of data. The next 4 digits are the address of where those 6 bytes of data are going to go. In this case, that address where they're going to go is at 0000. The next 2 digits are in this Intel Hex file are either going to be 00, meaning that it's data, or it's going to be 01, meaning that it's the end of file. After that, we see our data. So our data is actually 316140, and we can look over here. That corresponds with this, 316140, C30B01. Then the last 2 digits are the checksum for that line. So that's how we check for errors. We have a checksum at the end of every line. That's where that line ends. And that line ends because there's a little break in the memory. See, this one ended at 006, and the next line starts at 0008. So there's a little break in the memory. That's the end of that line. Our next line shows that there's 3 bytes of data. And this will start at 0008. So that corresponds over here. And our 3 bytes of data are going to be C35A00. So 00 means it's data, C35A00, and then the checksum. And that's the end of that little memory block. It's the end of that memory block because we've reserved this byte at 000B using the DS instruction, the DS pseudo opcode. So the next memory location is at 000C, and we can see that our next line of the Intel Hex file starts with a 20, and that's in hex. That's how many data bytes they're going to be. So there's going to be 32 data bytes. They're going to start at address 000C. The next 2 digits are 00, meaning it's data. So here's our data, CD4400, and we can see the data over here, CD4400. So all of this is contiguous memory. It fills these lines up completely. Each of them have 32 bytes of data. We could have up to 256 bytes of data because this could go up to FF. We have our 32 bytes of data, and then we have our checksum for each line. And then the next line, we can see the address. So this says there's another 32 bytes of data. Our address is 002C. So we can see each of those have gone up by 20 in hex. So 0C, 2C, 4C, 6C, 8C, AC, so forth. This is all contiguous. These are all full lines, meaning that it's contiguous memory. It goes all the way up until we get to this last little bit, which says there's 12 bytes. It's going to be at 0FEC. Let's go to our end of our program and look at that. 0FEC, so we're right here. So our data starts at D1, and it goes all the way through the rest of our program, and the last one is C9 down here. And then it has this checksum. Finally, you remember this line that we have to put in at the end of our assembler, this end. This isn't for the assembler. This is for the Intel Hex file. That end says it's the end of file. So we can see at the program counter 0FFE. So here we go at 0. This means that there's 0 data bytes in this line. The program counter is at 0FFE. Instead of being a 00, meaning it's data, this is a 01, meaning it's the end. And then there's our checksum. The programmer opens this hex file. Each of these lines has what address that data starts at for that particular line. Now let's look at the confidence test that we just had. And this, remember, starts at memory location 1000. So we can look at our hex file, and if we go down, we can see there was the little bit of version code that I had in lower memory. We can see at this line that there's 20 in hex bytes of data. They start at 1000. 00 means their data, and then it starts out F3,
goes all the way up to the 1C. So let's look. Here's our F3, our C304, and it goes up to the 1C, which is going to be at 101F. So here's the 1C, and then at 1020, it starts up with our CD. So here's 1020. Here's another file that's a little bit more complicated, and let's take a look at it. Let me go to the top of the file. This is a program that will simply load into a memory location the program counter followed by 16 data bytes going from 0F down to 00, followed by the announcement hello world. We see the first one here. We have an org statement, puts this at 1234 as our memory location, and this is just a test because I wanted to make sure that it will put the 1234 into memory in Big Endian. We could do this in Little Endian, but it's just a little easier when you're explaining it to have it in Big Endian. So this will take whatever the program counter is, put that in memory in Big Endian, and then it will have the 16 data bytes from 0F down to 00, and then hello world. After it does that one, it starts over at the beginning at 00, and it does the same thing over again, and it jumps up to 20, and then I just copied and pasted this a whole bunch of times. So it'll go through the entire 64K of memory, and at each 100 increment, it will put in the program counter followed by the same data. We can see the list file of this. So here's our 1234 for our program counter from our org. It put into memory at 1234, 1234, which is the Big Endian version of the program counter. Then it loaded up. Here's our 0F, ED, so we count down to 0 in hex, and then we have our hello world. Then the next statement, I started with an org at 0 again to back up again, and we have the exact same thing. Here's our program counter, 0000. Put the data in, and then it jumped up to 0100. Put the data in, jumps up to 0200, and it does this all the way up to FF00. And then the last bit is at FF1D, and then it has the end statement. Each of these have the same number of data bytes. They're 1D. Here's the first one. We set the program counter, so this is going to go into memory at 1234. The 00 means it's data. Here's our data, 1234, and then 0F all the way down to 00. And then we have our hello world. And then again, we have our checksum. Okay, so there's the line at 00. Here's the line that, this is the line that's at 1234. Here is our same thing at 00. Here's the same thing at 0100, 0200, 3, 4, 5, 6, 7. We can see the addresses go on up here. And so this is going to fill the entire 64K with that same little data block all the way up. Now let's open that with our programmer. If we open that with our programmer, we can see here's the block at 0000, and we have our program counter. We then have the 16 bytes that count down to 0. We then have hello world, and that's the end of that one. At 0100, here's our program counter, 0100, our 16 bytes and our hello world. This goes all the way up. And just like we expected, when we get to 0FFF, the buffer ends. But if we go over to a bigger device, so let's click on the device tab. Let's pick a different device. Let's pick one that can show us all 64K. And so that's the 27512. Go back to the buffer. And now we can see that we can go all the way up and we can stop anywhere. So this is 07F00. There's our block. There's our program counter, 7F00, 80. So this goes all the way up to FF00. And that's the last time that we've written this. So that's our full 64K full of that same little piece of data. Now we go back to our device, which is a 2732. And you see we're only now looking at that little block of data that ends at 0FFF. Or if we picked a 2716, we would only see half of that. Now this only goes up to 07FF. because we're just looking at that one little segment. But just like we did before, we can go back to our 2732. We then copy from a higher address. Remember, we want to copy from 1000 down to where we are now. We move A to B. Set it, moved OK. And now we can see that at EEPROM address 0, our program counter is 1000. We can do that again. We can copy from 2000 down to 100. Now we can see our program counter is at 200. So we could do that until we copied anywhere that we wanted to in system memory addressing down to our local EEPROM memory addressing. Now, as a final thing, I mentioned in an earlier video that the problem with the XGECU programmer is it has trouble with Intel Hex files. And what we will see is that if we open up that file in a 27512, so something that can hold the whole thing, bring it in, it has no problem bringing that in. Here's our data at 0, and we can look at our full 64K just like we could in the Willem programmer. But now if we pick a smaller chip, so let's pick a 2732, we select that, we open up the file, bring it in, and we can see it completely craps out. And what's happening is this very first line in the Intel Hex file that says go to address 1234 and put in this data. The XGECU software has no idea what to do because this device doesn't have that address. So this programmer doesn't know what to do. If we didn't have that particular line in, what we would do with this programmer is we would open up the file, and at this point we would say load the file from 1000 to the buffer at 000. So this is the offset. This is the same offset that should work over here, this offset here. This is the way we should be able to put in 1000 in that offset. And it should be able to load the file with that offset by simply skipping this first line. But unfortunately, this first line still messes it up. If we take that first line out, this works okay for loading the file with the offset. But the problem is this programmer still can't do 21. So I can't use it for my 2732s that have a 21 volt programming. Okay, well, that's all I had to say on this video. I hope you got something out of it, and I will talk with you later. Thanks for watching. Bye-bye.